We're going to talk about basically 4 different big periodic trends, and these are in chapter 5 if you want to, follow along or whatever. But we're going to start with something called atomic radius. Okay, atomic radius. What's the radius of anything? Right, the distance from what? That's right. The distance from the center of the circle to its outer. So I'm going to give you the definition here for atomic radius or atomic radii. When I say atomic radii, what's that mean? More than one. That's right. Okay. So atomic radius is half the distance. Oops. Between the nuclei of identical atoms that are bonded together. Okay, half the distance between the nuclei of identical atoms that are bonded together. So there's a reason that we look at atomic radius not just in terms of a single atom, but we look at it in terms of half the distance between 2 atoms. Okay? And this is kind of why if we have a single atom, let's say here's our nucleus, right? We've got electrons floating around here in our shells, right? We would think the radius is here to here. Would you agree? Okay. But do electrons necessarily stay in one place all the time? No, right? They're always moving. They're constantly in motion. So when we think about it in terms of 2, or the half the distance between 2 identical atoms, right? Here's the nucleus of each. Let's see here. I'll draw it kind of like this. Okay. Right? These shells might start to overlap when they bond. Right, these outer shells kind of start to overlap. So when we're talking about the distance or half the distance between these, we're looking nucleus to nucleus, and we would say this is our atomic radius, right? Or this is our atomic radius. Because when those 2 things start to overlap, it gives us a little bit more of a definite kind of distance from the center of our nucleus to the outer edge of our atom. Okay, so this just gives us kind of a locked position where that atom has to stay. Okay, so half the distance between the nuclei of identical atoms that are bonded together. So now I'm going to show you what the trend looks like. Okay, because all these trends show up on the periodic table. Okay, so the atomic radius trend, and I'm always going to draw my arrows in the direction of an increase. Okay, so it increases from right to left, and increases from up to down. Okay, so I'll draw this out. Increases from right to left, and it increases from up to down. Okay, so I always will draw my trends in the area of an increase, or in the direction of the increase. Right, so atomic radius is bigger on the left side of the periodic table and on the bottom side of the periodic table. Okay, so if you were just looking at your periodic table and you wanted to pick the one you thought had the largest atomic radius, what element would you choose? Which one? FR, right? Francium. Francium is the farthest to the left and the farthest down. Okay, so that would be one that we might choose to have the largest atomic radius. If we were looking at these trends, we might say that francium has the largest. Okay, so now I'm going to explain why that's the case. Why does it work like that? Okay, so these guys have a larger atomic radius, right? I'm just going to say large to small, or smaller at least. We decrease in atomic radius as we move this way because we see every time we move over an element, what happens to the number of protons? If we go from boron to carbon, what happens in terms of protons? We add one, right? And when we go from carbon to nitrogen, we add a proton. We add a proton, we add a proton. So as we work to the right, we're increasing the positive charge of our nucleus, right? We're adding protons, which means our nucleus, which is contained of protons and neutrons, Do neutrons give any charge? No. So our nucleus is not only getting bigger, it's getting more positively charged. And so what happens with that is as we get more positively charged, even though we get more electrons, the positive charge pulls those electrons tighter and tighter and tighter. Okay, so as you see an increase, so as we increase in protons, it pulls the electrons tighter. Okay, so that's the reason that these guys on the left side have larger atomic radius than the ones on the right side. Okay, and that's all within the same row. Okay, as we move down a row, it changes the story. Okay, but that's the reason for as we move, left to or right to left on the periodic table, we see a larger atomic radius because as we go the other way, those electrons are getting pulled tighter and tighter and tighter. Okay, so it's decreasing our atomic radius as we move to the right. Now, as we go down, what happens when you go down a row in the periodic table in terms of electrons? What are we adding? Do you remember? As we go down a group, what happens to our energy level? It gets higher, right? We increase. And so that increase in energy level means we add a shell. Okay, so as we add shells of electrons, that's automatically making our atom bigger. Right? So the reason for an increase as it goes down is that we're adding electron shells. Okay, so if you look on page 151, there's a chart there that has the atomic radius given in red. Okay? So at the bottom, you can see the atomic radius of each one. So which on here has our smallest atomic radius? Okay, we know it's got to be on what corner of the periodic table? The right and the upper or lower? Upper. So does helium have our lowest atomic radius? Yes. Right? Barely beating out hydrogen, right? Hydrogen adds a proton when it goes to helium, so it pulls them in a little bit tighter. So you see as you move down the periodic table, it goes again from biggest to smallest moving to the right. And you move down again, biggest to smallest, biggest to smallest, biggest to smallest. Okay, so there's a general trend that as we move to the left and move down, we would see an increase in atomic radius. Okay? Any questions with that one? Okay, so keep your book kind of propped open a little bit. We'll look at a couple other trends here. So if there's no other questions on atomic radius, we're going to move on to the second one. Okay, the next one is called ionization energy. The definition for ionization energy is the amount of energy required to remove the outermost electron from a neutral atom. Okay, so the ionization energy is kind of semi-related to the atomic radius. Okay, in fact, it's actually exactly opposite. Okay, so you'll see the trend for ionization energy increase as it goes to the right and as it goes to the top. Okay, and so I'm going to explain what each of these trends mean, but you'll see the largest ionization energies on the right side and near the top. Okay, and we're going to talk about why that might be. Okay, I want you to think if you might be able to understand why that might be, right? Ionization energy is the amount of energy that it takes to take an electron from its outer shell. Okay, so think about why that might be the case, that helium or fluorine or neon or those might have high ionization energies. Yeah, Evan?
For tighter together, so the harder the part.
That's right. That's right. We just talked about how the atomic radius, right? As we add protons, it pulls those electrons tighter and tighter, which means it's going to be much less likely to give it up, right? So the ionization increases as you move to the right, okay, for the same reason, okay? So more protons equals harder to pull off electrons, or harder to remove. Okay, and then for the reason that it's harder at the top than at the bottom, right, at these higher energy levels, down here, we see electrons are far from the nucleus. Oops. And that makes them easier to remove. So what do you think the lowest ionization energy would be? The easiest element to remove an electron from, what do you think? Okay, that would mean the lowest ionization energy. Which one? Francium, that's right. It's got the smallest atomic radius, so it's holding on to its electrons. I'm backwards. The biggest atomic radius, right? It's not holding on to them tightly at all. I was flip-flopped. Okay. So that means it's going to be easy to take an electron away from. So low ionization energy. So if you look at page 153 on that table on the bottom, these are listed ionization energies. Okay, and francium doesn't even have one listed because it's so likely to give away that electron that it's not difficult to pull it off at all. Okay, so the ones that have that little bar there, it's saying that the ionization energy is so low, or it's going to give away that electron so easily that it's not really considered an ionization energy at all. A short definition here for electron affinity, it's how likely an atom would be to accept an electron. So how likely an atom would be to accept an electron. Okay, so the real definition of electron affinity says the energy change that occurs when a neutral atom obtains an electron. Okay, so realistically what we're looking at here is how likely is an element to take an electron. Okay, so is there anything in particular on the periodic table that you think might have a high electron affinity? Any particular group or region or anything like that? Yeah, Hannah, what do you think? The S group, like this right here, would want to take an electron?
One right before it.
Okay. Which one?
Like one side right before it, like 9D or 1S.
9D or 1S. Oh, okay, like really specific. I'm talking about like just regions on the periodic table, maybe. Okay, really the group with the highest electron affinity are the halogens. Okay, because what do they need to complete their shell? One electron. So Evan, you're on the right path, right? We just want to think a little bit more general. So yeah, you're on the right track. Okay, the halogens just need one electron to complete their shell. So that's all they want to do is take one electron. So they're super likely to take on an electron. Okay, so halogens have the highest electron affinity. And then basically for electron affinity, you have much less defined trends than you did for all the other ones. But in general, you'll see an increase in electron affinity as you move to the right. Not a whole lot of trend up and down on the periodic table because it's kind of more about valence electrons than anything else. Okay? But you'll see that the halogens by far have the highest electron affinities. So if you turn to page 157, Okay, there's a table there, and the electron affinities are negative because there's an energy change that occurs, so they're taking on electrons, okay, which have negative charges. It has to do with energy and all that kind of stuff. But essentially what you're looking at is the biggest value of number, right? It doesn't have the negative. Don't let that part throw you off. So the largest electron affinities are all here in that halogen column. Okay, why do you think that the group 18s or the noble gases don't have an electron affinity listed? Yeah, Patrick.
They're already full of electrons.
They're already full, right? They already have a full shell. They don't need any more, right? They don't want to make it happen. Okay. All right, so any questions with electron affinity? And how likely they are to take an electron. That's basically it. Okay, and the ability of an atom in a chemical compound to attract electrons from another atom in that compound. Okay, the ability of an atom in a compound to attract electrons from another atom in the compound. And so the kind of everyday definition of electronegativity is how badly an atom wants an electron. Right? How badly does it want to take an electron from someone else? Okay, that's kind of the general definition, or what you should think of in terms of electronegativity is how badly does it want to take an electron from someone else? Okay? And so the trend for electronegativity is very defined and it's very simple. Okay? Electronegativity increases left to right and bottom to top, but to an exact point. Okay? So fluorine is our most electronegative atom. It wants to take electrons more than anyone else on the periodic table. Okay? And can we think about reasons why it might want to take electrons more than anyone else? How many valence electrons does fluorine have? 7. Good. And are its electrons close to the nucleus or far away from the nucleus? Close, right? So it's got 7 neutrons close to home, right? It wants that other one really, really, really badly. So fluorine is your most electronegative atom. It beats any other one on the periodic table. So the trend is essentially your electronegativity increases as you get toward fluorine. Right? The closer that you are to fluorine, the more electronegative you are. Okay, so in general, that's the trend. And you can look at the table on page 161. 161 gives you the values for electronegativity. And so every element has been assigned an electronegativity value. And it's basically a rating on how badly they want to take electrons from someone else. Okay, and these are abbreviated values. Fluorine's really electronegativity value, I think, is 4.19. Okay, so it's a little bit rounded up, I think, from what it is here. I could be wrong about that, but almost every single element is given an electronegativity value. How likely, how badly it wants to take electrons from other elements. So it all will just kind of point towards fluorine. The closer you get to fluorine, the more electronegative you are. Okay. And why don't you think most noble gases aren't given an electronegativity value? So why is that? All right, it doesn't want to attract, they don't want to attract other atoms or other elements, right? The lower noble gases you'll see have an electronegativity value. That's because they have something, they are getting into the D and the F orbitals, right? We're in the third energy level, so you have the D and the F orbitals, so they have more space for electrons. Okay, so they could take one if they really needed to or wanted to. Okay? Any questions here with any of our 4 periodic trends? Okay.